what if our variables, our x variables, are correlated? So, in the case of simple linear regression, we had three different assumptions. Now that we have several x variables, we have a fourth assumption, and that is that we should not have perfect multicollinearity. So let's see what that is. Well, the four squares assumptions, or four least squares assumptions in a multiple regression model, they are that the expectation of the residual given the values of the x variables should be equal to 0. This is just to say that no matter which level these x variables are at, the expected residual around the fitted line should be 0. So the residuals should be centered around the sample regression line. So and the second assumption is that the x variables are independent and identically distributed. Independent means that if you make one draw from the population to form your sample, then that one draw should not affect your second draw or any other draws. And identically distributed means that they are drawn from the same population, so they should have the same expected mean and variance every single time. But only in expectation. And the third least squares assumption is that large outliers should be unlikely, and that just means that they have finite fourth moments, finite kurtosis. Okay, so the fourth one is no perfect multicollinearity, and this is only for the multiple regression model. Okay, and what is this? Well, we say that x1 and x2 are perfectly multicollinear if x1 can be written as a linear function of x2. Okay, so for example, that is, we can write x1 as a constant plus a slope times the x2 variable, and here you can think about Celsius and Fahrenheit, two ways to measure temperature, right? And they always measure the same. Okay, so they are measuring the same but on different scales, right? So you can't include both of them, because if you do, then you can't really decipher which of these actually contains the information of temperature. Okay, so when x1 and x2 are perfectly multicollinear, we can't include both variables, because one way to think about it is that the slope, for example, we are looking at growth. For example, plant growth equals some intercept plus beta 1 times Celsius, degrees Celsius, plus, let's see, plus beta 2 times degrees Fahrenheit plus a certain residual containing all the other information that makes a plant grow. So, for example, the higher temperature, the more growth in certain ranges. But if you hold if you only want to increase degrees Celsius by 1 unit while holding degrees Fahrenheit constant, that's impossible, right? So these are so linked that you can't hold one constant while varying the other. So we cannot have a 1 unit increase in either of them to decipher what is the effect of a change. Another way to think about why this is a problem is that if you find that temperature, if you increase temperature by 1 degree, then you increase plant growth by 1 centimeter per week. Which of these betas is responsible for that effect? You can't decipher the difference, right? So this means that you can't really know the slopes of these. Maybe you could find the combined slope, but then you have to remove one of the variables or combine them. Okay, and combine them into one variable. So two other examples where we have perfect multicollinearity is here, where we have a regression model giving you the wage, and this wage is based on an intercept plus beta 1 coefficient times male, where male is a dummy variable for a man, and female is a dummy variable for a woman. Okay, so this is when male can be modeled as 1 minus female, because male and female, they are binary variables, right? So this is female is 0 if the person is a female, and male is 1 if no, female is 1 if it is a female. I should say 1 if 0 else, right? And male is 1 if male, 0 else, right? So you can model the male dummy variable by looking at the female dummy variable. So male is just 1 minus the female dummy variable. So they are perfectly multicollinear, and they contain the same information, which means they contain the same information. And this is also an example of the dummy variable trap, because here you have two categories, okay? You have male and female, and you have two dummy variables, okay? Male and female. which is wrong, because you should have one less dummy variables than you have categories. So for example, if you have one category for each day of the week, 7 days a week, then you only need 6 dummy variables, okay? And the 7th day is equal to the case when all the other dummy variables are equal to 0. So that would be the base case, right? So always have one less dummy variables then you have categories. Okay, a bit of repetition for most of you probably. Okay, so and if we estimate the wage equal the intercept plus beta 1 female plus UI using a sample consisting only of females, there will also be perfect multicollinearity. And you can get 5 seconds to pause the video and just think about why that is. Okay, so here you have wage equals to a constant, right, plus a constant times, well, female is only 1, right, times a beta 1. So you actually have 2 constants in the regression, which means that you cannot decipher which constant contains the information of the constant, right? So it's the same principle as in the previous example. So that's why you really need some variation in your data if you include some dummy variables. So why do we care about multicollinearity? Well, we care because if the 4 conditions or 4 assumptions hold, then we have a large sample size, we can use the central limit theorem. Then the OLS estimators of the intercepts and the slopes, or the intercept and the slopes, they are unbiased, which means that on average we get a result centered on the true result, true value of the intercept or the slopes. They are consistent, which means that if we have more data, then we should get a better result, and they should be jointly normally distributed. And the last one means that we can do some hypothesis tests. Okay, so what if the x variables are not perfectly collinear, but they have a correlation which is close to 1, close to plus or minus 1, we should say. Then we say that x1 and x2, we could say x1 and x2, they are imperfectly collinear. Okay, this correlation is just a measure of linear dependence between two variables. Okay. So, unlike perfect multicollinearity, if we have imperfect multicollinearity, we can still do our analysis, but we have a problem because our estimates of our betas, they will be quite imprecise. Just think about the model where you try to model plant growth by using temperatures on two different scales. There, it's impossible to decipher which beta contains the information of temperature. Okay, but if you have close to one correlation, then still it's really difficult to decipher which coefficient, which beta contains the information from that joint information pool of the two x variables. Okay, you can also think about holding or what is the coefficient, the sample slope, the beta 1 hat, the sample slope of the x1 variable. It's the effect of a 1 unit change in x1 on y. Okay, but if you do that, you have to hold the other x variables constant. So you're holding x2 constant. But if x1 and x2 are imperfectly multicollinear, then if you hold x2 constant, then you at the same time try to hold x1 constant. So as a result, there will be low variation in x1, and this low variance leads to less precise estimates of beta 1 hat. So you would, on average, get a result around the true value, the population value, but your estimates would be dispersed around that value with a high standard error, which means that the hypothesis test, to test whether or not this beta 1 hat, the sample slope, is different from a hypothesized value, like a null hypothesis, would be difficult. So, see you next time.